It's now 4:10. Oh, we're recording. Great. All right. Welcome, everyone. My name is Ken Goldberg, and we are at the Dream and CPAR seminar on Monday afternoon, and we're fortunate to be joined by Nathan Ratliff. He has a background from University of Washington. He did his PhD in robotics at Carnegie Mellon under Drew Bagnell. And he had then spent some time at Intel Labs. He's been at Google. He was at the Max Planck Institute, and then founded a company, Lula Robotics, that developed integrated systems for continuous reactive control. And then and maybe he'll mention something about that a little bit. And then he's now a distinguished research scientist at NVIDIA in their research group in Seattle. And I had the good fortune to hear him give a keynote talk on on geometric fabrics at Coral last fall, and it was really interesting, and I wanted to hear more and get more detail on it. So I'm really glad that he agreed to come today. And I think you're in for a treat. He's really a great speaker. So please welcome Nathan Ratliff. Nathan.
Hi. Yeah, thanks for inviting me. This is an exciting place to be giving a talk. So yeah, I'm going to be talking about geometric fabrics today, and really our effort in NVIDIA to develop tools for designing behavior. And some of this has gone into some of the simulation tools, and I'll be giving a little bit of an overview of that as well. Oops. There we go. So just as a motivational video, here's some of the tools that are currently using these behavioral dynamics. This version is called Riemannian motion policies. This is Isaac's Sim that we have here. It's a simulation tool that's built on top of the Omniverse toolkit. And this is just a series of videos that have been produced where the motion that's being generated here is built on top of Riemannian motion policies. And I'll be talking about that a little bit. Here's an example of one of the real world systems that we've put together. This is at the Seattle Robotics Lab here in Seattle, or where I am in Seattle. This demo specifically was one that was we brought to China and had on stage with Jensen at one of the keynotes. It's just a simple block stacking example with integrated simulation. You can see a camera off board and a camera on the arm. It integrates a lot of the perceptual tools that the lab's been putting together. Things like object detection and some tracking and stuff like that. Along with the underlying behavioral system is built on top of these behavioral dynamics, and that's how I was able to get the precision. There's obstacle avoidance that was very subtle, like avoiding the tower and things. It's all kind of able to do that integrated. Here's a series of demos that we've also produced in kitchen manipulation. Again, this is an integrated demo. This is as well on the KUKA hand, or KUKA arm and Allegro hand. Still using the same system. All of these things are actually using the same underlying control system. Different forms of perception, like this one uses a real-time algorithm called dense articulated real-time tracking. But all of it feeds into this control system that combines obstacle avoidance and low-level control, things like that. Oops, escaped. Okay, so one of the big ideas, the concepts that I'll be talking about is what we call strongly generalizing systems. That's what we strive for with these systems. We want systems that we can design using a collection of what you might call example scenarios that then generalize to an entire distribution of scenarios that you would actually see in deployment. And this is kind of a key concept behind real world robotics. We want to design these things in a lab or with learning tools or something like that, but when we get them out into the real world, whatever the world throws at it, we want the system to be able to solve. We want the systems to strongly generalize to those real world scenarios. And specifically, we're looking at areas of collaborative robotics up in Seattle. And this is where this notion of strongly generalizing systems really becomes important, because you don't just have an industrial setting where you can plan something very precise and have it work kind of day in and day out. But in collaborative systems, you're going to be interacting with kind of changing environments as well as people. Cats are going to jump up on the table and distract the robot. Like whatever the environment throws at it, you want the robot to be able to react to that. And so once designed, either trained or designed by hand, you want to put it in these environments and have it perform robustly. So here's an example of one of these systems. I think briefly this was shown in the other video, but it just is a more explicit version of it. So here we've designed this robot to basically play this game of closing the drawers. When me, human, can kind of play with the drawers, opening and closing them and stuff like that. And no matter what happens, we want the robot to be able to just constantly robustly close these drawers. And so you can't enumerate all of the different scenarios that the system will find itself in, but you want to be able to design a system that can robustly just solve anything that's thrown at it. No matter what the configuration of this thing is, where it finds itself, what configuration, its arms and stuff like that, it'll be able to navigate around this environment and close these things robustly. So in a sense, this is a little bit more of a local problem than the kind of general planning problem. But it's also something that requires this sort of strong generalization. If we put this out into the real world, in which case we did, we took this system and brought it down to GTC in one of the GPU technology conferences down in San Jose, and just had it running for hours. And it was able to robustly just do this thing kind of day in and day out. And so that's really what this technology that we're developing is aimed at. Okay, so if we want strong generalization, the big thing that enables it is what you would call highly compact behavior. So we want to be able to describe the behavior in a very small number of bits in a compact way, so that it in essence like exploits the structure of that behavior. Like statistical correlations between different solutions are in a sense exposed in very compact representations of that behavior. And so it has a stronger likelihood of generalization. And this is the same notion as like how minimum description length in machine learning promotes strong generalization in learning theory. And if we want kind of compact representation of behavior, kind of the go-to for many years has been cost functions. A cost function is an extremely compact representation of a bunch of different paths, essentially. So if you look at one of these cost functions here, like this thing in the middle here, between any pair of points, given that cost function, we now know how to decode a behavior which is optimal with respect to the cost function. You just run a planner, an optimal planner. And so this single cost function represents a bunch of different behavioral solutions, and then it ends up being very compact in that sense. And so what this means in terms of cost functions is that like this was work that I did a long while ago at this point, over a decade, about a decade and a half ago. You can learn behavior from a series of examples encoded as a cost function, and it generalizes really well. Like even at this point, if you are able to encode it into a cost function and decode it using a planner, we could build these into robust systems and robust planners that had the robots navigating outdoors and stuff like that. Those are really strongly generalizing encoding. You can build some theory around this based on structured prediction and imitation learning and stuff like that, but you can show that it's a really good generalizing behavior. Yeah, sorry. And you can go further and actually do like probabilistic representations of this. And in other words, like it's a really good representation. Cost functions are very expressive and they generalize really well. But one of the issues with cost functions, when you kind of go beyond these simple examples being kind of two-dimensional things where you can actually like run an optimal planner to something like this, where we have this high degree of freedom robot and a lot of obstacles and stuff like that, is that decoding complexity becomes an issue. So you might imagine different like planning architectures that you can put on this: task planning, motion planning, motion optimization, and you can build these kind of into different sets and run these as fast as possible. But in many cases, you often get maybe 10 hertz. And that's by simplifying the model significantly in order to kind of get to that speed. And that's because it's just a really difficult problem to take a cost function and actually decode a behavior like this. And so what we found in order to get the type of behavior that you see right there, where I'm actually interacting with the robot, pushing it around things, is that we had to fundamentally have all of this operating over the top of reactive control, something that can be incredibly reactive to these sorts of behaviors. And that's really because although the cost function is a really compact encoding, it's not particularly efficient in these high dimensional problems. Decoding the cost function into a behavior, which is an optimal policy, is really hard. And so we need to start, what we realized here is that we need to start looking into other sorts of representations that are both compact and efficient, that can be decoded quickly. And an example of that is actually this reactive control layer. We kind of stumbled across an instance of something that was necessary just by running these experiments. Okay, so that brings me to Riemannian motion policies. That was actually the motivation for developing out the theory of Riemannian motion policies. And actually a lot of that happened at Lula Robotics, our startup, which was ultimately acquired into NVIDIA to seed the SRL lab. And that was actually a really good example of necessity driving research. So like, after being at Max Planck, we developed a lot of MPC systems that were actually in the video that I was showing. And we were trying to kind of develop out the architecture behind that in Lula, these reactive systems. And what we found was critical was this reactive motion planning framework, or reactive control framework. And we started building out Riemannian motion policies, and that actually turned out to be a critical part of the system, which once we got to NVIDIA, we started exploring theoretically and building out the theory behind it. And so really the notion is there a more efficient encoding of behavior than cost functions? Cost functions, like I said, are incredibly compact, and so they generalize well, but you run into this fundamental limitation that it's very difficult to decode these things. Decoding in this case ends up being running an optimal planner. So like doing optimal control, motion optimization, and things like that, just motion planning, feeding into motion optimization, anything of that sort is part of the decoding process. And what we found is that in many cases, those things can be fairly brittle because the problem is just very difficult. It ends up being like a global optimization problem, which is really hard to solve from scratch every time you're given an example or a given instance of this. Oops, there we go. And so kind of the fundamental observation is that there are other ways of representing behavior. An example is like what you see here. Just like in Einstein's general theory of relativity, if you stretch space, geodesic curves actually curve around the contours of space in a highly nonlinear way. And if you do that right, and if you kind of describe the geometry of how obstacles in the environment might stretch the space and how that can transform into the configuration space, you can get a lot of very nonlinear behavior just by encoding into the fabric of the space. And that ends up being very compact because just like a cost function is kind of defined at the state level, how the space stretches, but it also ends up being incredibly efficient because decoding in this case, you don't have to solve a large-scale optimization problem. It just ends up being forward integration. So the better we can understand this, how obstacles might contribute to stretching of a workspace, which actually designs behavior, the more efficient we can make compact encodings of behavior. So our first step with this was just writing down differential equations and starting to study the structure of those differential equations and looking into how can we start deriving these or designing these things, like these behaviors by hand, so that they can express complex behavioral systems that can actually work really well in practice. A second part of this talk is going to be about how to take those ideas and actually build out a stronger theory behind them to kind of like fix some empirical problems that we saw here. But the first step was really kind of writing down the structure of these differential equations and trying to design them so we can get a kind of tangible feel for how they contribute to behavior. And that first step was what we call Riemannian motion policies, which is the technology that I showed in a number of the videos earlier on. And the high level is that these differential equations just being second order differential equations, where you map position and velocity to acceleration, they decompose in a nice way across transform trees of differentiable maps. So similar to like computational graphs in TensorFlow or PyTorch, you can build up networks of different spaces. For example, here Q is a configuration space. X1 might be a point on the end effector, X2 a point on the arm, X3 another point on the arm. You might have kind of other spaces extending from that, these little distance spaces to nearest obstacles. And in each one of these spaces, we can actually put a little piece of the differential equation and work out how that piece of the differential equation contributes to the whole. And there are close relationships between this and some classical operational space control, but what we are emphasizing here is the ability to write down both a policy in that space and a metric, which defines an entire spectrum of weights. This metric is a matrix, which for any position of velocity tells us what directions in the space does this policy care about. And then when you pull it back into the root using a particular type of mathematics and mathematical operations, the result ends up being a very intuitive, just metric weighted average of each of these policy components. And so this intuition allows us to design little pieces of the differential equations very intuitively, like obstacle avoidance, as well as like behavior shaping, end effector tracking, and stuff like that, and define kind of very nuanced metrics that define how these different components trade off among one another. So I just described this a little bit. I want to skip this math specifically. This is just some of the mathematics of how those combination operations, as well as like pulling them back into the root, can be derived. And here's an example of what one of these RMPs might be able to express. So if you think about obstacle avoidance, there's a lot of potential field methods that might be like pushing away from obstacles or optimal control methods and stuff like that. But one intuitive description of obstacle avoidance might be like, we have a position of velocity and a series of obstacles around us. If we look at both near obstacles that are near to us and obstacles that correlate with the direction of motion. So like number one here is both close and it the robot's kind of moving toward it. Whereas number two, it's also close, but the robot's kind of more orthogonal to that direction. And number three is both far away and orthogonal to the direction of motion. So number one really makes the difference. We should care about that a lot more especially the number 3, and number 2 is kind of in the middle there. And one hand-designed behavior that we might write down is to just damp the component of velocity in the direction toward those obstacles. So damp these little components here. And if you do, you kind of like remove the components of velocity that are pointing toward obstacles that really matter, and the system should just go around. And that's actually one of the RMPs that falls out from some of these derivations that we do. And that's how we're able to get the system to kind of like just flow around obstacles. And later on, I won't show a derivation of this, but later on, like you can actually derive this as more of a geometric perspective of how like the space is being warped by the obstacles, and that sort of behavior just falls out of that geometry. And so if we do this, kind of just put all this stuff together, hand design some RMPs and see what it can do. It can do some pretty expressive motion generation. So here we're just reaching toward a point. All of this is entirely local. It's not doing any planning. It's just reacting to the obstacles around it. And it's able to avoid these obstacles and just kind of like reach through these forest scenes here. I think I have another one. No. Well, here's, if we put it into basically a motion planning system with very simple heuristics, we can get instantaneous motion generation. We're doing no planning here. And we're even able to generate these things. It's using a depth camera to see where the obstacles are.
Nathan, we have a quick question in the comments from Forrest. He asks, what assumptions are you making about the dynamics of the system such that the ODE can be decomposed like this?
There's two answers to that. One is all of the systems that we're looking at currently are fully actuated. And so if you can invert the dynamics of your system and do feedback linearization, then the decomposition of the differential equation just falls out of the math of those forms of different equations. It's just kind of differential equations of the form x double dot, or acceleration equals some function of position and velocity. And the math of how they combine is just how we can define those in different spaces and look at how it contributes to a single differential equation with a root through a particular optimization problem. The second answer is that we're starting to look into how these interact with classical mechanics. So we can actually have underactuated systems and grab objects and deal with kind of the dynamics of the object and things as well. And it looks like it extends to that broader case pretty easily. Here's another example. Here we have it integrated with perception, so that every time we interact with the object, it's able to correct for it in real time. Because as it picks up the object and starts moving it, it actually starts controlling the object itself. So it controls the point on the bottom of the object. So like here, it's going to eventually grab the cup. And once it grabs the cup, it actually becomes part of the arm. And it's using a real-time tracker to track where that cup is relative to the end effector. So when I perturb it, it automatically immediately reacts to it. It's running these things at a kilohertz internally, so it's really the bottleneck is mainly perception there. And here's another example of being able to just lead the robot through the environment. It's doing automatic obstacle avoidance here, and I'm just kind of tossing it around. And this is one of the things that you can do. It kind of gives a more tangible feel for how these things can be used. So it's not doing any planning, but if you just guide it heuristically, it'll solve all of the problems locally, so that even very simple heuristic guidance is successful. And here's another example, just moving a little bit faster. This was actually pretty early on when we started playing with the ABB robot here. This is just me tossing the end effectors around in simulation and seeing what happens. And so all of this this movement of the arms for avoidance and things like that is automatically generated.
Well, I have a quick question. Maybe I missed this. You showed us examples of how this formulation helps you avoid obstacles, but just like in like potential fields, you can have like goal seeking, obstacle avoidance. Is the same process applicable here, where you can use the same formulation to not only avoid obstacles but also seek goals?
Yeah. It all depends on how you define the policy that's actually driving it. So like the obstacle avoidance is just trying to push away from things, but the in all of these examples, there's an end effector attractor that's pulling it toward a target, and these things are combining with each other pretty naturally. And so if you wanted to push onto an obstacle, we're actually starting to play with constrained formulations of this, where you can push onto the obstacle and just kind of slide across the surface and stuff.
Cool.
This is just another example of some manipulation. Okay, so now we're starting to get toward the second half of this. And the main thing, the kind of gap that we started seeing was that initial part was just, how do we get a feel for this? Like, what can we design by hand if we have these tools? But there's a gap between the empirical performance that we're seeing and both an explanation for that and a version of it that has some theoretical guarantees that might be like stability guarantees or guarantees of how different different parts of the difference equations combine together without kind of minimally affecting each other. And so early on in one of the original papers, we developed something called geometric dynamical systems, which is a version of this that is provably stable. But we kind of played with that a little bit, and it just proved challenging to tune by hand. And so a lot of the examples that we showed were actually a kind of earlier formulation that didn't have the stability guarantees. But kind of to push the stability research, we started looking into ways of learning these under the notion of maybe it was just difficult to tune by hand. But at some point we realized that there's actually a fundamental representational capacity limitation to some of these dynamical systems that we're deriving. And one example, I think there's a little bit of gap, so this may or may not make sense. But the type of dynamical system that we're playing with that was provably stable was essentially a classical mechanical system. So it had, it's kind of a generalization of the classical mechanical system that starts from the Lagrangian formulation, derives the behavior using the Euler-Lagrange equations. So in the same way, you can do this for classical mechanics, but it's a generalization of that. But the notion there was that the mass matrix of that mechanical system ended up being the priority matrix. And the behavior of it was derived from the Lagrangian itself. So as like these curvature terms, Coriolis terms, and stuff like that. And so if you look at those equations I showed earlier, there is two parts to an Riemannian motion policy. One is the policy, like what is the behavior that this space wants to do. The other one is the priority metric, which is how does it trade off with other policies in the space. And in these formulations of the stable system, both of those kind of came from the same place. We had to derive a Lagrangian whose equations of motion would produce both of those things. So it turns out that there is a kind of representational limitation to this, as in like you try to change the priority and it'll change the policy itself, and that becomes difficult. And kind of an example of this is these very simple classical mechanical systems. This came from some of the learning work that we did. It was learning from demonstration, where we have these example trajectories. And on the left, we see a differential equation that really is just built on one of them and is ignorant of the other examples. And on the right, we show a version of that where, oops, after learning the Riemannian metric of that space, this Riemannian metric is what ends up being the priority metric. But in this case, the Riemannian metric also plays the role of stretching the space. So after learning how to stretch the space right, this is the differential equation that we get. But kind of the intuition for where the issue is that that Riemannian metric plays two roles here. One, it stretches the space to give us the behavior that we want. And two, it's supposed to be the metric which defines the priority weights and how that policy should trade off with something else. And so if we wanted to combine this resulting policy with something else, we would have difficulty of trying to reweigh the metric, and it changes the behavior, and then change the behavior, and it changes the metric, and so on. And so that ended up being something that we wanted to get around. And that leads me to geometric fabrics. Like we started studying this problem and did realize that there is a fundamental representational capacity issue with those sorts of systems, and that led to a much broader formal class of differential equations, which really fleshed out the theory. So to start off with, some intuition of where these, or how these different classes of differential equations relate to one another. So RMPs by themselves, what you saw in those videos, they're incredibly powerful and flexible, but they're really guided by intuition. It takes some expertise to get the behavior you see. So really kind of a big part of this, this research is to analyze them, understand them, figure out a subset of those that are provably stable, that retain the same flexibility in terms of design as RMPs, but give you more concrete tools to use for design that's a little bit easier for novice designers. And so RMPs, you can kind of view it as the space of everything. Stable RMPs are a subset of that. My intuition, because I've been using these for so long, is pretty big, both within the stable range and kind of encompassing the space of RMPs. And so like the behavior that I'm able to get from this, from my colleagues, is pretty good in those demos. New users might have more difficulty kind of in that space, oops. And the problem is that some of these things are poorly understood and potentially dangerous. Like they don't have the stability guarantees, and so we have to figure out like how to capture really the space of RMPs that is largest, but also within the stable class. These geometric dynamical systems that I talked about are pretty good. They're stable, and they're kind of a good theory. And actually, classical operational space control sits in there. So it's actually already a good generalization of those things. But it's still relatively small relative to the space of RMPs that generate the behavior that empirically is what we're striving for. And so geometric fabrics, I view as kind of like the space here, which really captures both my intuition for how to design with these things, but also provides a stable, concrete, and well understood tool for behavioral design. Let's see. I'm going to skip through this a little bit faster. I think I talked about some of this already. This is just talking about the limitations of the earlier parts. So what we developed was something called optimization fabrics. Optimization fabrics are the broad space of these differential equations. You can think of them intuitively as starting with a nominal behavior, like this here. This nominal behavior, there we go. This nominal behavior is just a differential equation that defines like what the system wants to do in the absence of anything else. And in particular, it's what we call unbiased, as in the system comes to a rest, that fabric itself isn't trying to push the system anywhere. And importantly, if we optimize over the top of it, if we force it with a potential function, negative gradient of a potential function, we're guaranteed to minimize that potential function. So in a sense, an optimization fabric is this unbiased nominal behavior differential equation that can act as an optimization medium for optimizing potentials. So a potential function, you can imagine a number of different optimization algorithms to run on it. In this case, it's going to be a differential equation where the underlying fabric pushes it around and kind of affects the way it descends down toward the medium. So it kind of adds behavior on top of the optimization process. And the fabric is the thing that's going to be designing the behavior. And the optimization process, the fact that there's a minimum that we're striving for and we're guaranteed to get there, is going to characterize the stability properties of this. So here's an illustration of that. You place a potential here and it forces the system across the fabric, and it ends up being biased by the fabric, but also optimizing that potential. And categorically, these things I've been calling geometric fabrics are going to be a type of optimization fabric built on non-Riemannian nonlinear geometries. So an example of this, I won't go through the details of the math here, but a high-level example is a classical mechanical system. Classical mechanical system, like if you're not forcing with a potential function, like gravity or something else, it just defines a behavior, which you can kind of visualize as like a behavior of the end effector in space, let's say, like there's no gravity or something, where if it's not moving, it's not moving. If you push it, it'll kind of move with some behavior. And you can force it with a potential function and add some damping, and it's guaranteed to get to the minimum of that potential function. And so that's an example of an optimization fabric. In this case, it's specifically actually a geometric fabric because there's this duality between classical mechanics and Riemannian geometries, and specifically a Riemannian geometric fabric. So the fabrics that we're going to design are ones that are called geometric fabrics, and they're built on this notion of generalized nonlinear geometries of paths. And they're going to allow us to define behaviors as collections of paths. And the main idea here is just that if you look at velocity of a trajectory and acceleration of a trajectory, one varies by delta t squared, another or delta t, and the other one varies by delta t squared. So if you scale the time variable of this thing by some factor, then the acceleration is going to scale by that factor squared, which means that if you just write down a differential equation that has that property, you scale velocity and it scales the acceleration by the scalar squared, then it's going to generate integral curves, paths that are generated by integration that are always consistent with each other, independent of the velocity that you choose. Because if you scale the velocity that you're moving at by some factor, it automatically scales the acceleration to compensate for that so that you stay along the same path. And so any differential equation that has this property, which is called homogeneous to degree 2, that the scaling the velocity scales the acceleration by the scalar squared, will have this path consistency, which is very geometric. Like behavior is defined by the paths and not by the specifics of like how fast you're moving along those things. And so here's an illustration of path consistency. And this ends up being nice for describing behavior because we can speed up and slow down along these differential equations without changing the actual behavior. So here, for each one of these dots, we shot it off through a particular differential equation, a geometric differential equation at 2 different velocities. And you'll see like one path just goes faster than the other, but they're both overlapping entirely. So like the dark one is one of the shootings and the light one is the other one. So what this means is that if we define behavior based on these geometries, we have this flexibility to choose what the velocity profile is going to be. And if we have that flexibility, that means we can speed up and slow down in such a way that we can conserve some notion of energy. So if we have some metric of energy that we've written down, we can speed up and slow down in such a way that that energy is conserved without actually changing the behavior. And that what that means is through this, what we're calling an energization transform of the differential equation, we can take the geometry describing the behavior and turn it into something that has some metric of energy that can measure whether or not we're optimizing in some way. So it's like if it's conserving energy and then we constantly bleed it off, then that energy just decreases over time and eventually gets to a minimum. And so we can turn any arbitrary behavior described as this geometry of paths into something that has this stability property characterized by conservation of energy and reduction of energy over time. Here's what I just described. The notion of the energization transform is really just like speeding up and slowing down along the direction of motion so that it conserves a particular notion of energy. And one of the interesting things that we found, I mentioned earlier that these systems that I described, where we're deriving the behavior from a Lagrangian, would have kind of a coupled policy and weight metric. What you can show is that by doing this energization transform, it's equivalent to taking that system and actually bending it to align with this external nonlinear geometry so that it represents the same metric, which is the priority weight, but then embodies this separate geometry to act as the policy. So we can define a policy as this nonlinear geometry, take an energy Lagrangian to define a metric, and just combine the two by kind of bending them to align with one another.
I have a slightly high level question. So some of the concepts you've been talking about here remind me of like control Lyapunov functions or control barrier functions. Mm-hmm. What are the sort of like connections or differences between sort of CLF as a way of like thinking about stabilizing a system that has control input and sort of your take on this? Yeah.
Those are good ways of designing stable systems. What we're focusing here on is a theory of systems that we can design by these nonlinear geometries. And so kind of the focus is on being able to shape the behavior of this system using nonlinear geometry and use what are essentially classical Lyapunov principles to prove stability on top of it. Does that answer your question?
Yeah, thanks.
Okay, cool. And this kind of illustrates that a little bit more concretely. The notion has always been to be able to kind of like blend a bunch of these things together so that they combine into a system that's provably stable, but captures like a lot of different types of behavior. So here we're just incrementally designing a geometric fabric layer by layer, just kind of layering piece by piece on top of the previous ones without touching the previous ones, and looking at how the behavior combines, how it still converges to a target, and how each new component affects the resulting behavior. So we start with this Euclidean behavior, which is just straight line. If we choose a target and try to optimize over the top of it, it ends up bending that behavior to hit that target. We can then add joint limit avoidance, basically, kind of a boundary here, and just layer it on top of the previous one, do the same thing, and we get behavior that it's a little subtle here, but it's bending a little bit more to get there. And then here we've added an obstacle, and now we end up with obstacle avoidance. In this case, we're ending just random vortex geometries, which is possible because we can just write down these geometries and then doing the same, and it's kind of bending these all over the place, but still converging to the target. And here we're shaping the behavior at the end to be a little bit more straight as it approaches the target. So it's able to be affected by these vortices and then converge to a straight line behavior at the end. I'm going to skip these in lieu of time and just go directly to this one. This is an example of all of these things coming together. As I described, kind of layering behavior on top of each other to implement this simple bin picking example. And the notion here is to start off with like very simple behaviors. In this case, it's straight line between targets, and then layer on top of it, bit by bit, more and more sophisticated behavior until it can solve that problem. The second part here, I'm just skipping forward a little, is not doing obstacle avoidance, but doing a very simple behavior of pushing out of obstacle and then dragging it toward a target, and really trying to solve the kind of global navigation problem, like that end-to-end thing right there. And finally, the last part is adding obstacle avoidance. And in each case, we fixed the behaviors before and just layered on a new behavior on top of it. So we can just like design this thing layer by layer until we get this this version here. Then we ran a series of robustness tests. Let's see, on how well this generalized to novel situations. Like here, we've changed the base rotation, skipping forward. Move things around a little bit more, like kind of just changing the base around and stuff.
There's a quick question in the comments about the incremental slide that you had, where you incrementally building the fabric. The question's from Victoria, and she asks, if you're doing this incrementally, do you get the same final fabric if you were to incrementally add things in a different order?
Yeah. Everything ends up being a metric weighted average, and so it kind of retains that commutativity property of just averaging. Here's one thing that I didn't mention, but because this is a geometry, we also are able to get consistent speed control. We can, like I said before, for the stability stuff, we can speed up and slow down along the direction of motion without actually changing the behavior. And so that allows us to separately actually control a particular speed of like the end effector and configuration space and stuff like that, and retain the stability properties. I'm going to skip through this a little bit. The basic notion there is that all of these things end up having the same form as Riemannian motion policies, and we can kind of pull in the same architecture. It's just a subclass of those things which are much better understood and have better geometric properties, including like weighing each other together and stuff. And that's about it. The high level now is that we're in the process of building this into a full system with our stack and replacing the Riemannian motion policy, so we can do things like these behaviors with those. And with that, I can take any questions. Thanks.
Great, thank you, Nathan. You know, this is, it's really seems surprising that you're able to get this. And I'm just wondering, I'm feeling like there must be a catch somewhere, or maybe there isn't. But you know, in terms of the motion, I mean, there's no sense of necessarily smoothness, right? I mean, and there's no minimum. They're not minimum length trajectories, are they, or does that also come with this?
No, the smoothness comes from the fact that we're designing second-order differential equations, and so things are smooth in terms of the differential equation itself, and so the accelerations are smoothly changing, and so the behaviors that you see are
Okay, so you get that for free. I mean, that comes out.
Yeah.
And the minimality, I mean, because when you say about geodesics, these are minimal paths too?
Minimal with respect to the geometry that you've designed. And so that can be arbitrarily long in like configuration space or end effector space. Like you can have a geometry that lifts up and goes down like that. But there's parts of that. One is like designing those geometries is actually fairly straightforward. And it's easy to kind of like design those even in like a lower dimensional space, like the end effector space, that can pull it back into the configuration space. But two, we've been doing a lot of work recently on how do we learn these things, so that if we did want to characterize like shortest path in some way or kind of like shortest time, we can use this as a parameterization of policies, which has a very strong inductive bias. Kind of the heuristic is that like because we're able to design these things so easily and flexibly, this architecture and these tools constitute a strong inductive bias for policy representation. We're starting to get some pretty neat results with learning in that context in terms of data efficiency. Okay, great. And very exciting. Okay, are there any other questions? Because we should wrap up, but we can, Nathan, maybe you can put your email address on the in the chat so that we can, someone will follow up with you. And some of this, this has been published, and is there a GitHub or some of the code that's shared, or? The code isn't available yet.
Okay.
There's a version of the code. There's a workshop paper that we have out. This is work with the University of Washington as well as Byron's group on something called RMP squared, which is an implementation of these tools using TensorFlow computational graphs and stuff. That isn't available code-wise yet, but the paper is out, and we're going to be making the code available pretty soon.
Great, thank you. All right, good. So everyone, you can reach Nathan. Nathan, you're gonna put your email just in that chat real quick before we sign off. That way we can get everybody. And then you can please ask them other questions. And I wish we had a better way of applauding at the end. We might be able. If I say unmute, we'll get that. But it always is very weak compared to the real thunderous applause that you would get in person. So apologize for that, Nathan, but thank you so much for coming and being here today. We look forward to seeing more of you and following up in the future.
Yeah, thanks for inviting me.
All right.
Let me know if you have any questions.
Take care. Bye.
Thanks. Bye-bye.